The glory effect. First, alien rainbow. What if alien worlds have their own unique versions of rainbows that follow completely different rules of physics? We're familiar with the colorful arcs that appear in Earth's skies after a rainstorm when sunlight hits water droplets at just the right angle. But on a planet where it rains molten iron instead of water, could similar optical effects exist? Astronomers recently discovered something extraordinary on WASP 76b that suggests the answer is yes, and it reveals surprising similarities between Earth's atmosphere and this hellish world. On Earth, rainbows form when sunlight enters water droplets, bends as it passes through, reflects off the back, and bends again as it exits. This process separates white light into its component colors, the familiar red, orange, yellow, green, blue, indigo, and violet arc we recognize as a rainbow. Humans have observed and documented this phenomenon for thousands of years. But in 2023, astronomers detected signs of a completely different optical phenomenon on WASP 76b, something called a glory effect. Glories represent another fascinating optical phenomenon observable on Earth, appearing as colorful concentric rings of light rather than arcs. Unlike rainbows, glories form through diffraction, where light waves bend as they pass through or around small particles. On Earth, glories typically appear when an observer is positioned with their back to the sun, looking down at clouds or fog. You might see colorful rings surrounding the shadow of your head, or an airplane when flying above clouds. The same physical process creates colored rings, sometimes visible around streetlights on foggy nights. What does a glory on a world of molten iron really look like? This question bridges our familiar Earth experiences with the alien environment of WASP 76b, where the same physical principles operate under radically different conditions. In a groundbreaking discovery, researchers analyzing data from the James Webb Space Telescope detected light patterns from WASP 76b that match what we'd expect from a glory effect. The telescope captured the specific wavelength patterns and intensity distributions characteristic of glory formation, strongly suggesting this optical phenomenon occurs in the atmosphere of this distant world. This detection required extraordinary precision. The glory signature represents a tiny fraction of the total light coming from the WASP 76b system. Scientists had to carefully account for the light from the star, other atmospheric effects, and potential instrumental artifacts to isolate the glory pattern. This discovery represents the first optical phenomenon of this kind ever detected outside our solar system. While astronomers have previously observed glories in Venus's atmosphere, identifying one on a planet 637 light-years away demonstrates the remarkable capabilities of modern astronomical instruments and analysis techniques. This finding is particularly surprising given the extreme conditions on WASP 76b. The glory effect requires specific atmospheric conditions to form. The particles scattering the light must be nearly perfectly spherical, uniform in size, and stable enough to be observed over time. The star needs to shine directly at the planet, with the observer positioned just right to capture the reflected light. This rare combination of requirements explains why this is the first glory detected outside our solar system. What makes this discovery fascinating is what it tells us about the fundamental nature of physics across the universe. Despite the radical differences between Earth and WASP 76b, one a temperate world with water-based weather, the other an ultra-hot planet with metal rain, both produce similar optical phenomena governed by the same physical principles. The laws of light diffraction work identically, whether the particles are water droplets or exotic materials in WASP 76b skies. If you could somehow witness this glory effect, on WASP 76b you would see something both familiar and alien. The basic pattern of colorful concentric rings would resemble Earth's glories, but the specific colors, intensity, and size would differ based on the composition of the atmospheric particles creating it. The glory might appear around the shadow of any object in the right position, creating a corona-like effect against the alien landscape. The wavelengths of light in WASP 76b's glory provide clues about the particles creating it. While Earth's glories form from water droplets, WASP 76b's glory must form from materials that exist as small spherical droplets in its atmosphere, potentially iron droplets or other metallic or silicate compounds. The glory effect requires droplets that are extremely uniform in size and nearly perfectly spherical. This suggests highly specific conditions in WASP 76b's atmosphere, allowing for the formation of such consistent particles. The temperature, pressure, and compositional environment must be stable enough to produce these uniform droplets repeatedly, challenging assumptions about how chaotic such an extreme world might be. This discovery provides a new tool for studying distant worlds, as the specific properties of a glory effect can reveal detailed information about the particles creating it. The wavelengths, intensity patterns, and other characteristics help scientists determine the size, composition, and distribution of particles in an exoplanet's atmosphere, information difficult to obtain through other methods. The detection of a glory effect on WASP 76b suggests that despite its alien composition, atmospheric physics works fundamentally similarly across the universe. This universality of physical laws provides a framework for understanding even the most extreme environments in our galaxy. The specific requirements for glory formation provide new constraints on atmospheric models and reveal details about the planet's weather systems that previous observations couldn't detect. This optical phenomenon offers a window into the structure and dynamics of an atmosphere existing under conditions impossible to recreate in Earth laboratories, potentially reshaping our understanding of planetary physics more broadly.